Welcome to my channel Online Biology Tutorials. In this live of today, we will be reading Chapter 11 Electricity of Class 10 Science taken from NCERT, which is being followed in the CBSE board. In case you are interested in hearing the audio of first 10 chapters, a playlist has already been uploaded. I hope the screen is clear and visible. The orientation is also correct. So let's begin with the reading of Chapter 11 Electricity. Electricity has an important place in modern society. It is a controllable and convenient form of energy for a variety of uses in homes, schools, hospitals, industries, and so on. What constitutes electricity? How does it flow in an electric circuit? What are the factors that control or regulate the current through an electric circuit? In this chapter, we shall attempt to answer such questions. We shall also discuss the heating effect of electric current and its applications. 11.1 Electric current and circuit. We are familiar with air current and water current. We know that flowing water constitutes water current in rivers. Similarly, if the electric charge flows through a conductor, for example, through a metallic wire, we say that there is an electric current in the conductor. In a torch, we know that cells or a battery, when placed in proper order, provide flow of charges or an electric current through the torch bulb to glow. We have also seen that the torch gives light only when its switch is on. What does a switch do? A switch makes a conducting link between the cell and the bulb. A continuous and closed path of an electric current is called an electric circuit. Now, if the circuit is broken anywhere or the switch of the torch is turned off, the current stops flowing and the bulb does not glow. How do we express electric current? Electric current is expressed by the amount of charge flowing through a particular area in unit time. In other words, it is the rate of flow of electric charges. In circuits using metallic wires, electrons constitute the flow of charges. However, electrons were not known at the time when the phenomenon of electricity was first observed. So, electric current was considered to be the flow of positive charges, and the direction of flow of positive charges was taken to be the direction of electric current. Conventionally, in an electric circuit, the direction of electric current is taken as opposite to the direction of the flow of electrons, which are negative charges. Coming on to the next page. If a net charge q flows across any cross section of a conductor at time t, then the current I through the cross section is I is equals to q by t. The SI unit of electric current is coulomb or C, which is equivalent to the charge contained in nearly 6 into 10 to the power 18 electrons. We know that an electron possesses a negative charge of 1.6 into 10 to the power minus 19 C. The electric current is expressed by a unit called ampere or A, named after the French scientist André Marie Ampere, born in 1775 and died in 1836. 1 ampere is constituted by the flow of 1 coulomb of charge per second. That is 1A is equals to 1C by 1S. Small quantities of current are expressed in milliampere. 1 milliampere is equals to 10 to the power minus 3 ampere, or in microampere. 1 microampere is equals to 10 to the power minus 6 ampere. An instrument called ammeter measures electric current in a circuit. It is always connected in series in a circuit through which the current is to be measured. Figure 11.1 shows the schematic diagram of a typical electric circuit comprising a cell, an electric bulb, an ammeter, and a plug key. Note that the electric current flows in the circuit from the positive terminal of the cell to the negative terminal of the cell through the bulb and ammeter. So the first numerical of this chapter, electricity. Example 11.1. A current of 0.5 ampere is drawn by a filament of an electric bulb for 10 minutes. Find the amount of electric charge that flows through the circuit. We are given I is equals to 0.5 ampere, T is 10 minutes or 600 seconds. So Q is equal to IT. So placing the values, so you'll get the answer as 300 coulombs. In text questions, question number 1. What does an electric circuit mean? Define the unit of current. Calculate the number of electrons constituting 1 coulomb of charge. Next topic, 11.2, electric potential and potential difference. What makes the electric charge to flow? Let us consider the analogy of flow of water. Charges do not flow in a copper wire by themselves, just as water in a perfectly horizontal tube does not flow. If one end of the tube is connected to a tank of water kept at a higher level, such that there is a pressure difference between the two ends of the tube, water flows out of the other end of the tube. For flow of charges in a conducting metallic wire, the gravity, of course, has no role to play. The electrons move only if there is a difference of electric pressure called the potential difference along the conductor. This difference of potential may be produced by a battery consisting of one or more electric cells. The chemical action within a cell generates the potential difference across the terminals of the cell. Even when no current is drawn from it, when the cell is connected to a conducting circuit element, the potential difference sets the charges in motion in the conductor and produces an electric current. In order to maintain the current in a given electric circuit, the cell has to expend its chemical energy stored in it. We define the electric potential difference between 2 points in an electric circuit carrying some current as the work done to move a unit charge from one point to another or to the other. Potential difference or V between 2 points, work done W by charge or Q. So V is equals to W by Q. The SI unit of electric potential difference is volt or V, named after Alessandro Volta, born in 1745 and died in 1827, an Italian physicist. 1 volt is the potential difference between 2 points in a current carrying conductor when 1 joule of work is done to move a charge of 1 coulomb from one point to the other. Therefore, 1 volt is equals to 1 joule by 1 coulomb, or 1 V is equals to 1 J C minus 1, means 1 joule by coulomb. The potential difference is measured by means of an instrument called the voltmeter. The voltmeter is always connected in parallel across the points between which the potential difference is to be measured. Example 11.2. How much work is done in moving a charge of 2 coulomb across 2 points having a potential difference of 12 volts? Solution. The amount of charge Q that flows between 2 points at potential difference V is equals to 12 volt is 2 coulomb. Thus the amount of work or W done in moving the charge is W is equals to V into Q. So after putting the values you will get 24 joules. In text question 1, name a device that helps to maintain a potential difference across a conductor. 2. What is meant by saying that the potential difference between 2 points is 1 volt? 3. How much energy is given to each coulomb of charge passing through a 6-volt battery? 11.3, circuit diagram. We know that an electric circuit, as shown in figure 11.1, comprises a cell or a battery, a plug key, electrical component, or they could be many. So that's why bracket is there in the component, and connecting wires. It is often convenient to draw a schematic diagram in which different components of the circuit are represented by the symbols conveniently used. Conventional symbols used to represent some of the most commonly used electrical components are given in table 11.1. So all the symbols are given. Here you need to see the book and you need to practice also. So the symbols are given for an electric cell, a battery or a combination of cells, plug key or switch which is open should be drawn like this, plug key or switch if it is closed should be drawn like this, a wire joint is shown like this, and wires crossing without joining are shown like this. Next page. I hope the screen is completely visible and clear. Electric bulb is shown like this. A resistor of resistance R is shown like this. Variable resistance or rheostat is shown by any of these ways. Ammeter like this, voltmeter like this. So we are coming to the important part of this chapter, electricity. Ohm's law 11.4. If there is there a relationship between the potential difference across a conductor and the current through it? Let us explore with an activity. Activity 11.1. Set up a circuit as shown in figure 11.2 consisting of a nichrome wire XY of length say zero point 0.5 meter, an ammeter, a voltmeter, and four cells of 1.5 volt each. Nichrome is an alloy of nickel, chromium, manganese, and iron metals. First, use only one cell as the source in the circuit. Note the reading in the ammeter I for the current and the reading of the voltmeter V for a potential difference across the nichrome wire XY in the circuit. Tabulate them in the table given. Next, connect two cells in the circuit and note the respective readings of the ammeter and voltmeter for the values of current through the nichrome wire and the potential difference across the nichrome wire. Repeat the above steps using three cells and then four cells in the circuit separately. Calculate the ratio of V to I for each pair of potential difference V and current I. So here you are required to fill this table by your observations that they have asked for. So ultimately, we have reached page number 176 of your NCERT and we are reading electricity chapter. In this activity, you will find that approximately the same value for V by I is obtained in each case. Thus, the VI graph is a straight line that passes through the origin of the graph, as shown in figure 11.3 means this one. Thus, Thus, V by I is a constant ratio. In 1827, German physicist George Simon Ohm, born in 1787 and died in 1854, found the relationship between the current I flowing in a metallic wire and the potential difference across its terminals. The potential difference V across the ends of a given metallic wire in an electric circuit is directly proportional to the current flowing through it provided its temperature remains the same. This is called Ohm's law. In other words, V is directly proportional to I, or V is divided by I is equals to a constant. So that constant is R, so V is equals to I R. In equation 11.4, R is a constant for the given metallic wire at a given temperature and is called its resistance. It is a property of a conductor to resist the flow of charges through it. The SI unit is ohm, represented by the Greek letter this one. According to the Ohm's law, we have R is equals to V by I if the potential difference across the two ends of the conductor is 1 volt and the current through it is 1 ampere, then the resistant R of the conductor is 1 ohm. That is 1 ohm is equals to 1 volt by 1 ampere. Also from equation 11.5 we get I is equals to V by R. It is obvious from equation 11.7 that the current through a resistor is inversely proportional to its resistance. If the resistance is doubled, the current gets halved. In many practical cases, it is necessary to increase or decrease the current in an electric circuit. A component used to regulate current without changing the voltage source is called variable distance. In an electric circuit, a device called rheostat is often used to change the resistance in the circuit. We will now study about electrical resistance of a conductor with the help of the following activity. Activity 11.2. Take a nichrome wire, a torch bulb, a 10-watt bulb, and an ammeter, a plug key, and some connecting wires. Set up the circuit by connecting four dry cells of 1.5 volt each in series with the ammeter, leaving a gap XY in the circuit as shown to you here in this figure. Complete the circuit by connecting the nichrome wire in the gap XY, plug the key, note down the ammeter reading, take out the key from the plug. Note always take out the key from the plug after measuring the current through the circuit. Replace the nichrome wire with the torch bulb in the circuit and find the current through it by measuring the reading of the ammeter. Now repeat the above step with the 10-watt bulb in the gap XY. Are the emitter readings different for different components connected in the gap XY? What do the above observations indicate? You may repeat this activity by keeping any material component in the gap. Observe the emitter readings in each case, analyze the observations. In this activity, we observe that the current is different for different components. Why do they differ? Certain components offer an easy path for the flow of electric current, while the others resist the flow. We know that motion of electrons in an electric circuit constitutes an electric current. The electrons, however, are not completely free to move within a conductor. They are restrained by the attraction of the atoms among which they move. Thus, motion of electrons through a conductor is retarded by its resistance. A component of a given size that offers a low resistance is a good conductor. A conductor having some appreciable resistance is called a resistor. A component of identical size that offers a higher resistance is a poor conductor. An insulator of the same size offers even higher resistance. So we are here 11.5 factors on which the resistance of a conductor depends. Activity 11.3, complete an electric circuit consisting of a cell, an emitter, a nichrome wire of length L, say marked L, and a plug key as shown in figure 11.5 means this one. Now plug the key, note the current in the emitter, replace the nichrome wire by another nichrome wire of same thickness but twice the length, that is 2L marked 2 in the figure 11.5. Note the emitter reading. Now replace the wire by a thicker nichrome wire of the same length L marked 3. A thicker wire has a larger cross-sectional area. Again, note down the current through the circuit. Instead of taking a nichrome wire, connect a copper wire marked 4 in figure 11.5 in the circuit. Let the wire be of the same length and the same area of cross section as that of the first nichrome wire marked 1. Note the value of the current. Notice the difference in the current in all cases. Does the current depend on the length of the conductor? Does the current depend on the area of cross section of the wire used? Next, it is observed that the emitter reading decreases to one half when the length of the wire is doubled. The emitter reading is increased when a thicker wire of the same material and of the same length is used in the circuit. A change in emitter reading is observed when a wire of different material of the same length and the same area of cross section is used. On applying Ohm's law, as seen in equations 11.5 and 11.7, we observe that the resistance of the conductor depends on its length, on its area of cross section, and third, on the nature of its material. Precise measurements have shown that resistance of a uniform metallic conductor is directly proportional to its length L and inversely proportional to the area of cross section A. That is, R is directional proportional to L, so R is proportional to 1 by A. Combining both the equations, we will get R is directly proportional to L by A. R proportional sign can be replaced by using the sign rho L by A. So where P like rooking, so it's a rho. Greek symbol is a constant of proportionality and is called the electrical resistivity of the material of the conductor. The SI unit of resistivity is ohm meter. It is a characteristic property of the material. The metals and alloys have very low resistivity in the range 10 to the power minus 8 ohm meter to 10 to the power minus 6 ohm meter. They are good conductors of electricity. Insulators like rubber and glass have resistivity of the order of 10 to the power 12 to 10 to the power 17 ohm meter. Both the resistance and resistivity of a material vary with temperature. Table 11.2 reveals that the resistivity of an alloy is generally higher than that of its constituent metals. Alloys do not oxidize or burn readily at high temperatures. For this reaction, they are commonly used in electrical heating devices like electric iron toasters, etc. Tungsten is used almost exclusively for filaments of electric bulbs, whereas copper and aluminium are generally used for electrical transmission lines. Table 11.2. is showing you the electrical resistivity of some substances at 20 degrees Celsius. So conductors are silver, copper, aluminium, tungsten, nickel, iron, chromium, mercury, manganese, and this is their resistivity being given. Alloys are constantan, alloy of copper and nickel, manganene, alloy of copper, manganese, and nickel. Nichrome is an alloy of nickel, chromium, manganese, and iron. Insulators, glass, hard rubber, ebonite, diamond, paper, dry. Example 11.3. How much current will an electric bulb draw from a 220-volt source if the resistance of the bulb filament is 1200 ohm? How much current will an electric heater coil draw from a 220-volt source if the resistance of the heater coil is 100 ohm? So to calculate this part A, we are given V is equal to 220 volts and resistance 1200 ohm. So we can use the equation 12.6 and we can calculate I by placing the values as 0.18 ampere. So for part B, we are already having V and R with us. So using equation 11.6, we can calculate I as 2.2 ampere. Note the difference of current drawn by an electric bulb, an electric heater from the same 220-volt source. Let's come to another page. Here we have another numerical example 11.4. The potential difference between the terminals of an electric heater is 60 volt. When it draws a current of 4 ampere from the source, what current will the heater draw if the potential difference is increased to 120 volt? So we know that V is equal to 60 volt and current is 4 ampere. So according to the Ohm's law, we can calculate resistance as 15 ohm. When the potential difference is increased to 120 volts, the current is given by V by R. Placing the values will get the answer at 8 ampere. So current through the heater becomes 8 ampere. Example 11.5. Resistance of a metal wire of length 1 meter is 26 ohm at 20 degrees Celsius. If the diameter of the wire is 0.3 millimeter, what will be the resistivity of the metal at that temperature? Using table 11.2, predict the material of the wire. So solution is we are having the resistance as 26 ohms, diameter is 0.3 millimeter, we can convert it into meter, length is 1 meter. So we know that rho is equals to RA by L. Further simplifying RA as because it's the area, so we'll be placing the values and rho will come up to be 1.84 into 10 to the power minus 6 ohm meter. So resistivity of the metal is 20, at 20 degrees Celsius is 1.84 into 10 to the power 6 ohm meter. So from table 11.2, we see that this is the resistivity of manganese. Example 11.6. A wire of the given material having length L and area of cross section A has a resistance 4 ohm. What would be the resistance of another wire of the same material having length L by 2 and the area of cross section as 2A? So R1 is equals to rho L by A. We will get value as 4 ohms. Now for the second wire, we will be simplifying it as rho L by 2 upon 2A. So it will come up to be 1 by 4 R1. So R2 is 1 ohm after simplification. Now we have in-text questions. On what factors does the resistance of a conductor depend? Will current flow more easily through a thick wire or a thin wire of the same material when connected to the same source? Why? Let the resistance of an electric component remains constant while the potential difference across the two ends of the component decreases to half of its former value. What change will occur in the current through it? Fourth, why are coils of electric toasters and electric irons made of an alloy rather than a pure metal? Five, use the data in table 11.2 to answer the following. A, which among iron and mercury is a better conductor? B, which material is the best conductor? Next topic 11.6. Resistance of a system of resistors. In preceding sections, we learned about some simple electric circuits. We have noticed how the current through a conductor depends upon its resistance and the potential difference across its ends. In various electrical gadgets, we often use resistors in various combinations. We now therefore intend to see how Ohm's law can be applied to combinations of resistors. There are two methods of joining the resistors together. Figure 11.6 shows an electric circuit in which three resistors having resistance R1, R2, R3. They're talking about these respectively are joined end to end. Here the resistance are said to be connected in series. This is one way to connect the resistors. Figure 11.7 shows a combination of resistors in which three resistors are connected together between points X and Y. Here the resistors are said to be connected in parallel. So they are looking parallel to each other. So the connection of the resistors is parallel only. 11.6.1 Resistors in series. What happens to the value of current when a number of resistors are connected in series in a circuit? What would be their equivalent resistance? Let us try to understand this with the help of following activities. Activity 11.4 Join three resistors of different values in series. Connect them with a battery, an emitter, and a plug key as shown in figure 11.6. You may use the resistors of values 1 ohm, 2 ohm, 3 ohm, etc. and a battery of 6 volt for performing this activity. Plug the key, note the emitter reading. Change the position of emitter to anywhere in between the resistors. Note the emitter reading each time. Do you find any change in the value of current through the emitter? You will observe that the value of the current in the emitter is the same independent of its position in the electric circuit. It means that in a series combination of resistors, the current is the same in every part of the circuit or the same current through each resistors. Activity 11.5 In activity 11.4, insert a voltmeter across the ends X and Y of the series combination of three resistors as shown in figure 11.6. Plug the key in the circuit and note the voltmeter reading. It gives the potential difference across the series combination of resistors. Let it be V. Now measure the potential difference across the two terminals of the battery. Compare the two values. Take out the plug key and disconnect the voltmeter. Now insert the voltmeter across the ends X and P of the first resistor as shown in figure 11.8. So every time whenever they are referring to, you should practice drawing this. Plug the key and measure the potential difference across the first resistor, let it be V1. Similarly, measure the potential difference across the other two resistors separately. Let these values be V2 and V3 respectively. Deduce a relationship between V, V1, V2 and V3. You will observe that the potential difference V is equal to the sum of potential differences V1, V2, V3. That is, the total potential difference across a combination of resistors in series is equal to the sum of potential difference across the individual resistors. That is, V is equals to V1 plus V2 plus V3. In the electric circuit shown in figure 11.8, let I be the current through the circuit. The current through each resistor is called I. It is possible to replace the three resistors joined in series by an equivalent single resistor of resistance R, such that the potential difference V across it and the current I through the circuit remains the same. Applying the Ohm's law to the entire circuit, we have V is equals to IR. So on applying the Ohm's law to the three resistors separately, we further have V1 is equals to IR1, V2 is equals to IR2, V3 is equals to IR3. So from the equation 11.11, IR is equals to IR1 plus IR2 plus IR3. So overall, it is going to be R1 plus R2 plus R3. We can conclude that when several resistors are joined in series, the resistance of the combination Rs equals the sum of their individual resistances R1, R2, R3 and is thus greater than any individual resistance. Example 11.7 An electric lamp whose resistance is 20 ohm and a conductor of 4 ohm resistance are connected to a 6-volt battery as shown in figure 11.9. Calculate the total resistance of the circuit. B. The current through the circuit and C. The potential difference across the electric lamp and conductor. So solution, the resistance of an electric lamp R1 is equals to 20 ohm. The resistance of the conductor conducted in series R2 is equals to 4 ohm. So total resistance will be R1 plus R2. After putting the values, you'll get 24 ohms. The total potential difference across the two terminals of the battery V is equals to 6 volt. Now by Ohm's law, the current through the circuit is given by I is equals to V by R. So it will become 6 volt divided by 24 ohm is equals to 0.25 ampere. Applying Ohm's law to the electric lamp and conductor separately, we get potential difference across the electric lamp. So V1 is equals to 20 ohm into 0.25 ampere. We'll get 5 volt as the answer. And that across the conductor V2 will be coming after putting the values as 1 volt. Suppose that we like to replace the series combination of electric lamp and conductor by a single and equivalent resistor. Its resistance must be such that a potential difference of 6 volt across the battery terminals will cause a current of 0.25 ampere in the circuit. The resistance R of this equivalent resistor would be R is equals to V by I. So after putting the values, it will come up as 24 ohm. This is the total resistance of the series circuit. It is equal to the sum of the two resistances. In text questions, draw a schematic diagram of a circuit consisting of a battery of three cells of 2 volt each, a 5 ohm resistor, an 8 ohm resistor, and a 12 ohm resistor, and a plug key, all connected in series. Redraw the circuit of question 1. Putting in an ammeter to measure the current through the resistors and a voltmeter to measure the potential difference across the 12 ohm resistor. What would be the readings in the ammeter and the voltmeter? 11.6.2 resistors in parallel. Now let us consider the arrangement of three resistors joined in parallel with the combination of cells or a battery as shown in figure 11.7, the earlier one. Activity 11.6, make a parallel combination XY of three resistors having resistances R1, R2, R3 respectively, connected with a battery, a plug key, and an ammeter as shown in figure 11.10. Also connect a voltmeter in parallel with the combination of resistors. Plug the key and note the ammeter reading. Let the current be I. Also take the voltmeter reading. It gives the potential difference V across the combination. The potential difference across each resistor is also V. This can be checked by connecting the voltmeter across each individual resistor as seen in figure 11.1. Take out the plug from the key, remove the ammeter and voltmeter from the circuit, insert the ammeter in series with the resistor R1 as shown to you in this figure. Note the ammeter reading I1. Similarly, measure the currents through R2 and R3. Let these I2 and I3 respectively. What is the relationship between I1, I2, and I3? The only student who is listening to this live. Thank you so much for joining. It is observed that the total current I is equal to the sum of the separate currents through each branch of the combination. So it is going to be I is equals to I1 plus I2 plus I3. Let R P be the equivalent resistance of a parallel combination of resistors. So by applying the Ohm's law to the parallel combination of resistors, we have I is equals to V by RP. On applying Ohm's law to each resistor, we have I1 is equals to V by R1, I2 is equals to V by R2, I3 is equals to V by R3. So after using the equations 11.15 and 17, we will get 1 by Rp is equals to 1 by R1, 1 by R2 plus 1 by R3. Thus, we can conclude that the reciprocal of the equivalent resistance of a group of resistances joined in parallel is equal to the sum of reciprocals of the individual resistances. Example level 11.8 in the circuit diagram given in figure 11.10, suppose the resistors R1, R2, R3 have the values 5 ohm, 10 ohm, 30 ohm respectively, which have been connected to a battery of 12 volt. Calculate A, the current through each resistor, the total current in the circuit, and C, the total circuit resistance. So solution can be calculated as R1 is equals to 5 ohm, R2 is equals to 10 ohm, and R3 is equals to 30 ohm. Potential difference across the battery V is equals to 12 volt. This is also the potential difference across each of the following resistor. Therefore, to calculate the current in the resistors, we use Ohm's law. So the current I1 through R1 is equals to V by R1. I1 after putting the values will come as 2.4 ampere. Next page, the current I2 will be coming as 1.2 ampere by putting the values. I3 will come as zero point 0.4 ampere. So I will be sum total of I1, I2, I3. After putting the values, we'll get 4 ampere. So the total resistance RP will come out to be, by this equation, RP will come out to be 3 ohm, 11.9. If in figure 11.12, R1 is given as 10 ohm, R2 40 ohm, R3 30 ohm, R4 20 ohm, R5 60 ohm, and a 12-volt battery is connected to the arrangement, calculate A, the total resistance in the circuit, and B, the total current flowing in the circuit. Solution. Suppose we replace the parallel resistors R1 and R2 by an equivalent resistor of resistance R dash. Similarly, we replace the parallel resistors R3, R4, and R5 by an equivalent single resistor of resistance R double dash. Then using the equation 11.18, we have 1 by R dash is equals to 1 by 10 plus 1 by 40. So it will come out to be 8 ohm. Whereas R double dash can be calculated by putting the values as 10 ohm. Thus the total resistance will become 18 ohm after adding R dash and R double dash. So to calculate the current, we can use the Ohm's law. After putting the values, we'll get the answer as 0.67 ampere. We have seen that in a series circuit, the current is constant throughout the electric circuit. Thus, it is obviously impractical to connect an electric bulb and an electric heater in series because they need currents of widely different values to operate properly. Another major disadvantage of a series circuit is that when an component fails, the circuit is broken and none of the component works. If you have used fairy lights to decorate buildings on festivals, on marriage celebrations, etc., you might have seen the electrician spending a lot of time in trouble locating and replacing the dead bulb. Each has to be tested to find which has fused or gone. On the other hand, a parallel circuit divides the current through the electrical gadgets. The total resistance in a parallel circuit is decreased as per equation 11.18. This is helpful particularly when each gadget has different resistance and requires different current to operate properly. We have in-text questions now. 1. Judge the equivalent resistance when the following are connected in parallel. A 1 ohm and 10 to the power 6 ohm. B 1 ohm and 10 to the power 3 ohm and 10 to the power 6 ohm. 2. An electric lamp of 100 ohm, a toaster of resistance 50 ohm, and a water filter of resistance 500 ohm are connected in parallel to a 220 volt source. What is the resistance of an electric iron connected to the same source that takes as much current as all three appliances, and what is the current through it? What are the advantages of connecting electrical devices in parallel with the battery instead of connecting them in series? How can three resistors of resistances 2 ohm, 3 ohm, and 6 ohm be connected to give a total resistance of A 4 ohm, B 1 ohm? 5. What is A, the highest, B, the lowest total resistance that can be secured by combinations of four coils of resistance 4 ohm, 8 ohm, 12 ohm, 24 ohm? 11.7. Heating effect of electric current. We know that a battery or a cell is a source of electrical energy. The chemical reaction within the cell generates a potential difference between its two terminals that sets the electrons in motion to flow the current through a resistor or a series of resistors connected to the battery. We have also seen in section 11.2 that to maintain the current, the source has to keep expending its energy. Where does this energy go? A part of the source energy in maintaining the current may be consumed into useful work, like in rotating the blades of an electric fan. Rest of the source energy may be expended in heat to raise the temperature of the gadget. We often observe this in our everyday life. For example, an electric fan becomes warm if used continuously for longer time, etc. On the other hand, if the electric circuit is purely resistive, that is, a configuration of resistors only connected to a battery, the source energy continually gets dissipated entirely in the form of heat. This is done as the heating effect of electric current. This effect is utilized in devices such as electric heater, electric iron, etc. Consider a current I flowing through a resistor of resistance R. Let the potential difference across it be V. Let T be the time during which a charge Q flows across. The work done in moving the charge Q through a potential difference V is VQ. Therefore, the source must supply energy equal to VQ in time T. Hence, the power input to the circuit by the source is P is equals to VQ by T. It will come out to be VI, or the energy supplied to the circuit by the source in time t is P into T, that is VIT. What happens to this energy expended by the source? This energy gets dissipated in the resistor as heat. Thus, for a steady current I, the amount of heat H produced in time t is H is equals to VIT. Applying Ohm's law, equation 11.5, we get H is equals to I square RT. This is known as Joule's law of heating. The law implies that heat produced in a resistor is directly proportional to the square of current of a given resistance, 2 directly proportional to resistance of a given current, and 3 directly proportional to the time for which the current flows through the resistor. In practical situations, when an electric appliance is connected to a known voltage source, equation 11.21 is used after calculating the current through it using the reaction I is equals to V by R. The student who is hearing to this live, thank you. Are you from class 10th? Example 11.10. An electric iron consumes energy at a rate of 840 watt when heating is at the maximum rate, and 360 watt when the heating is at the minimum. The voltage is 220 volt. What are the current and the resistance in each case? For study purpose. Okay, thank you. I have read your reply. Dear, I have also recorded the audio of first 10 chapters in case whenever you are requiring at the time of revision, you can use them. I have also recorded the explanatory video series of heredity chapter with the word problems, and I have explained life processes too. So from the equation 11.19, we know that power input is P is equals to VI, thus the current I is equals to P by V. So A can be calculated when heating is at the maximum rate. So I, after putting the values, comes out to be 3.82 ampere, and the resistance of the electric iron R is equals to V by I. So it can be calculated as 57.6 ohm. When heating is at the minimum rate, I can be calculated as 1.64 ampere after placing the values. And the resistance of the electric iron can be calculated with the help of the formula R is equals to V by I. So it will come out to be 134.15 ohm. Example 11.11. 100 joule of heat is produced each second in a 4 ohm resistance. Find the potential difference across the resistor. So these are the values which are given. You need to calculate. So you can calculate with the help of this formula. I is equals to under root H by RT. After placing the values, we'll get the answer as 5 ampere. Thus, the potential difference across the resistor V is equals to IR. After putting the values, it comes out to be 20 volt. In text question 1. Why does the cord of an electric heater not glow while the heating element does? Compute the heat generated while transferring 96,000 coulomb of charge in 1 hour through a potential difference of 50 volt. An electric iron of resistance 20 ohm takes a current of 5 ampere. Calculate the heat developed in 30 seconds. 11.7.1 Practical application. of heating effect of electric current. The generation of heat in a conductor is an inevitable consequence of electric current. In many cases, it is undesirable as it converts useful electrical energy into heat. In electric circuits, the unavoidable heating can increase the temperature of the components and alter their properties. However, heating effect of electric current has many useful applications. The electric laundry iron, electric toaster, electric oven, electric kettle, and electric heater are some of the familiar devices based on Joule's heating. The electric heating is also used to produce light, as in an electric bulb. Here, the filament must retain as much of the heat generated as its possible so that it gets very hot and emits light. It must not melt at such high temperature. A strong metal with high melting point, such as tungsten, melting point is 3380 degrees Celsius, is used for making bulb filaments. The filament should be thermally isolated as much as possible using insulating support, etc. The bulbs are usually filled with chemically inactive nitrogen and argon gases to prolong the life of the filament. Most of the power consumed by the filament appears as heat, but a small part of it is in the form of light radiated. Another common application of Joule's heating is the fuse used in electric circuits. It protects circuits and appliances by stopping the flow of any unduly high electric current. The fuse is placed in series with the device. It consists of a piece of a wire made of a metal or an alloy of appropriate melting point. For example, aluminium, copper, iron, lead, etc. If a current larger than the specified value flows through the circuit, the temperature of the fuse wire increases. This melts the fuse wire and breaks the circuit. The fuse wire is usually encased in a cartridge of porcelain or similar material with metal ends. The fuses used for domestic purposes are rated as 1 ampere, 2 ampere, 3 ampere, 5 ampere, 10 ampere, etc. For an electric iron which consumes 1 kilowatt electric power when operated at 220 volt, a current of 1000 by 220 ampere, that is 4.54 ampere, will flow in the circuit. In this case, a 5 ampere fuse will be used. 11.8 electric power. You have studied in your earlier class that the rate of doing work is power. This is also the rate of consumption of energy. Equation 11.21 gives the rate at which electric energy is dissipated or consumed in an electric circuit. This is also termed as electric power. The power P is given by P is equals to VI, so P will become V square by R. The SI unit of electric power is watt or W. It is a power consumed by a device that carries 1 ampere of current when operated at a potential difference of 1 volt. Thus, 1 watt is equals to 1 volt into 1 ampere or 1 VA. The unit watt is very small. Therefore, in actual practice, we use a much larger unit called kilowatt, which is equal to 1000 watts. Since electrical energy is the product of power and time, the unit of electrical energy is therefore watt hour or WH. 1 watt hour is the energy consumed when 1 watt of power is used for 1 hour. The commercial unit of electric energy is kilowatt hour or kWh, commonly known as unit. So kWh is equals to 1000 watt into 3600 seconds, so which comes out to be 3.6 into 10 to the power 6 joules or J. For study purpose, as you have read the thumbnail, this is just the audio of electricity chapter. So I usually take live every day and I take some part for explanation as well, but this is solely a reading video. Many people think that electrons are consumed in an electric circuit. This is wrong. We pay the electricity board or electric company to provide energy to move electrons through the electric gadgets like electric bulb, fan, and engines. We pay for the energy that we use. Example 11.12. An electric bulb is connected to a 220 volt generator. The current is 0.5 ampere. What is the power of the bulb? So we know that power can be calculated as P is equals to VI. So after putting the values, it comes out to be 110 watt. Next example Example 11.13, an electric refrigerator rated 400 watt operates 8 hours per day. What is the cost of the energy to operate it for 30 days at rupees 3 per kilowatt hour? So we can calculate this as the total energy consumed by the refrigerator in 30 days would be 400 watt into 8 hour per day for 30 days. It comes out to be 96 kilowatt hour. Thus, the cost of energy to operate the refrigerator for 30 days is 96 kilowatt hour into rupees 3 per kilowatt hour. So, after multiplication, it comes out to be rupees 288. In text question 1, what determines the rate at which energy is delivered by a current? 2, an electric motor takes 5 ampere from a 220 volt line. Determine the power of the motor and the energy consumed in 2 hours. So here we have the summary of the chapter. A stream of electrons moving through a conductor constitutes an electric current. Conventionally, the direction of current is taken opposite to the direction of flow of electrons. The SI unit of electric current is ampere. To set the electrons in motion in an electric circuit, we use a cell or a battery. A cell generates a potential difference across its terminals. It is measured in volts or V. Resistance is a property that resists the flow of electrons in a conductor. It controls the magnitude of the current. The SI unit of resistance is ohm. Ohm's law, the potential difference across the ends of a resistor is directly proportional to the current through it, provided its temperature remaining the same. The resistance of a conductor depends directly on its length, inversely on its area of cross section, and also on the material of the conductor. The equivalent resistance of several resistors in series is equal to the sum of their individual resistances. A set of resistors connected in parallel has an equivalent resistance Rp given by 1 by Rp is equal to 1 plus R1 plus 1 upon R2 plus 1 upon R3. The electrical energy dissipated in a resistor is given by W is equals to V by I into T. The unit of power is watt. 1 watt of power is consumed when 1 ampere of current flows at a potential difference of 1 volt. The commercial unit of electrical energy is kilowatt hour, represented as kWh. 1 kilowatt hour is equals to 3 into 3, 6 and 5 zeros. So it is coming to be 36 lakh joules, which can also be written as 3.6 into 10 to the power 6 joules. So with this, we are done with the reading of a lengthy chapter in one go. And this is chapter number 11, Electricity of class 10 science, taken from NCERT. In case this was helpful, do share it with your friends. You can subscribe if it was meaningful to you. There are certain videos more in the playlist, and they will be coming each day in a live every evening. Stay connected. See you in next video. Thank you.